All right, I hope you guys did really well in your AP exams, and for those who didn't make today's class, here is today's lesson, 13.5, the area problem slash the integral. I'm going to kind of give you a lot of background here and then work out a couple examples. It's a pretty long lesson, so if I may have to put this in 2 different videos, so bear with me. All right, so we're going to be dealing with area. So let's take, for example, I gave you some point A, some point B. And if I were to use some, I don't know, let's call this some value k. And if I were to actually create a function y equals k, right, here's my function y equals k, and then use the interval, so just from A to B, and I ask you to find this area right here, you could do this really easily. I mean, it's a rectangle. You know that a rectangle area is base times height. Now, the height of this triangle, would you agree, is just k value, right? That's the height of this triangle. And then, what is the base, rectangle, and what's the base of this rectangle? The base of this rectangle is really b minus a, right? So if this was 5, this was 1, 5 minus 1 is 4. That would be the distance of that. So to find the area of something as simple as this rectangular shape in a coordinate system, it's just going to be the base, b minus a, times the height, times k. What if we were to get a little bit more complicated with our function? Okay, this was our function here. I'm going from A to B, for example, and instead of just having a horizontal function, maybe I have a function that's at an angle. Okay, again, this is some line, so we'll call this y equals f of x. Now, if I said, all right, from A to B, and of this function that's given here, what if I wanted to find the area of this? Now, this is a trapezoid in disguise. I'm actually going to turn my paper so you can see this. Do you see that this is really a trapezoid where we've got our 2 bases? I don't know if you remember, but the area of a trapezoid is the average of the bases, so b1 plus b2 times a half, times the height. And you see how this is actually the height of, because it's a right angle, the height of this trapezoid? So if I was going to now actually find the area of this trapezoid, I need to know, number 1, the height. The height, again, is still just b minus a. That would be the height of this. And then I need to know the lengths of these bases. Now, this height, would you agree that this height is really f of a? If I were to plug a into this function, I'd get out this point. That would be how high it is, right? This would be f of a. And the length of this, if I plug b into this function, I'd find out that this is f of b. That's how high this is. So if I was going to find the area of this trapezoid, or of this, this trapezoidal shape, I'd have 1/2 times my 2 y values added together times the base, which is this b minus a. Okay? Now, you could do this without even this formula. If I just gave you numbers, you could easily do this. You could find out how tall this is, average them, and then times the length of this if you had numbers. I want you to start seeing the notation because we're going to use that later on. What if, so now what you're going to meet is, you can do this with any type of polygonal, however you say that word, shape. If I gave you a rectangle, a trapezoid, even an octagonal shape, you could break things up into rectangles and triangles and find the area. But let's say now, you now meet something called a curve. And I said, all right, if I went from A to, let's go here, B, and I said, I want to find the area under this curve. I want to know what is the area under this curve? Now, you have not met this, and welcome to calculus. This is what calculus does. So what the first thing that you're going to be introduced to in this class, and then you'll get into obviously much more greater detail next year in calculus, is how to actually approximate this value. So what we're going to talk about right now is actually approximating the area under a graph of a function. That's what we're going to do right now. We're going to approximate it, okay? Now, we do this by doing something called partitioning, which partitioning is really just dividing. So what we're going to do is we're going to divide this area, this distance, which we're going to divide the interval from A to B, right? This is really what I want to do. I want to divide this distance, this length of information from A to B into equal sub-intervals. So I'm going to divide this into little pieces, and I'm then going to find the area of the little pieces and add them all up. Okay? So there's two ways to do this problem, and I'm going to show you I'll show you both ways. So working with this graph right here, okay, I'll call this type A. What I'm going to do is I'm going to partition this. I'm going to divide this into two sub-intervals. Okay? Two perfectly equal pieces. So if I was going to divide this into two perfectly equal pieces, that would be right about there, right? So if I were to divide this, there's my half. Now, the distance from here to here would be exactly the same as the distance to here because they're equal. How much would this piece be? This piece would be, right, from here to here, this piece would be b minus a over 2. And then this piece from here to here would be b minus a over 2, right? It's this whole distance cut in half, divided by 2. Now, the first method of actually approximating, we're not finding the actual area, but approximating this area, is what we can do is choose left endpoints. So I'm going to take these two subdivisions, and I'm going to take each of the sub-intervals and use the left piece and divide it into these little rectangular pieces. So here's my left, right, I've got these two pieces. Here's the left endpoint, and I'm going to draw a horizontal line, and I'm actually going to use this value right here to find the area. And then on this piece, I'm going to use, here's my other left endpoint, and I'm going to find this area. Now, if I was going to find these areas, now again, I'm approximating. Here's my base, b minus a over 2, and then I need to know my heights. Well, isn't the height would be whatever this amount is, this a, when I plug it into my function, that this would be f of a, correct? Now, what we stopped doing is we stopped using a's and b's because how do you describe this point here? So what we actually do is we start, or at least this book, starts using u's, and they say, all right, this is my first piece, this is my second piece. They divide the intervals into u's. So this height of this rectangle would be f of u sub 1. I want to know how tall this is, this point on my graph. This would be if I plugged u in the function. This height here, technically, would be f of u sub 2. Now, to find the actual area of this guy, I would have the area of this one plus the area of this one. So the area of this one would be f of u sub 1 times this b minus a over 2 plus f of u sub 2 times this b minus a over 2. And that would find me the area of these two guys. Now, do you notice that because I chose left endpoints, do you think that this overestimates or underestimates this graph? If you think underestimates, you're absolutely right. I mean, this is going to give us an amount that's not exact, but it's probably under the actual amount. Okay? Now let's see, I'm going to give you a second example of how we can do this, but this time on this graph, and let me shove this up a little bit. This time on this graph, I'm going to take a similar graph, I don't know, just make something up. And this time, so I'm going from A to B is my interval. And this time instead, I'm going to break it into 4 equal parts. Actually, you know what, I may move this over one more, just since make it easier for myself. I'm going to divide this into 4 intervals, so 4 sub-intervals, excuse me, sub-intervals. Okay, so if I divide this into 4 sub-intervals, there's my halfway mark, there's my quarterly mark, meaning I'm now going to make 4 rectangular pieces in here. And instead of using left endpoints, I'm actually going to use right endpoints here. So for each of my sub-intervals, I'm going to go to the right side, and I'm going to draw a horizontal line. So from here, I'm going to draw my horizontal line. From this point on my graph of this interval, I'm going to draw my horizontal line. And from this one, I'm going to draw my horizontal line. So now what I'm actually going to do is I'm going to find the area with right endpoints of these rectangular pieces. Now, looking at this, can you tell me, is this going to overestimate or underestimate my actual area underneath the curve? Overestimate, absolutely, you're right. So, but before, I'm showing you this technique, okay? I'm just showing you a technique here. So if I was going to actually try to find this length, the base of this rectangular period, how much is that? Well, it's this amount, so b minus a, divided by how many intervals? So there were 4 intervals. So each of these pieces is b minus a over 4. Each of the bases, b minus a over 4. And then again, since we're using the right endpoints, this is my first height, right? This is the actual height I'm using. So this is my u sub 1. This is my u sub 2, because this is the second height that I need. Here's my third height, and here's my fourth height. So this would be u sub 3, u sub 4. And again, I'd find my area by taking my base times my height, and my height would be plugging in this u into my function. Okay? So some things that I think you should just kind of have in your notes is, number 1, that left endpoints are going to be underestimates, and right endpoints are overestimates. All right? Now, can you imagine, okay, take for a moment, that as I continue to take an interval such as a to b, and instead of breaking it up into 4 sub-intervals, I break it up into 10. Or what if I break it up into 100? What do you think happens to my approximation in terms of the area under the graph? If you think that it actually gets closer and closer, it approaches the actual accurate area under this curve, then you're absolutely right. The more intervals we have, the more accurate we're going to be, regardless if we're using left endpoints or right endpoints. It really doesn't matter. So what I want you to write is, as the sub-intervals increase, so the more sub-intervals I have, if I have 10, 100, 1000s, approximations to the actual area improve. Okay, they actually improve. All right. The first thing I'm going to show you, so I'm going to skip to another page. The first thing I'm going to show you is a simple problem where instead of a curve, we actually have a kind of a straight line. So here's example number 1. Okay, I'm going to write out all the questions. This is like a 6-question part. So the first thing is they're going to give you the function. They're going to say f of x equals 4x. Okay, and they're going to tell you it's defined over the interval of 0 to 6. Okay, and I'm going to switch my graphs for just a moment because I'm going to save some time and just show you the work that I've already done. So we're going to take the function f of x equals 4x, and it's defined over the interval, on the interval 0 to 6. And then here are the 6 questions that they're going to give us. The first thing they're going to say is graph the function. All right, I'll show you that in a moment. Super easy. B, they're going to say approximate the area by partitioning this interval into 3 subintervals using left endpoints. So the first thing they want us to do is approximate the area with 3 subintervals with left endpoints. The next thing they're going to do is do the same thing with 3 subintervals, but now with right endpoints. Then they want us to now increase our subintervals to 6 intervals using left endpoints, doing 6 intervals with right endpoints. Oops, there should be a T. And then they want us to actually find what is the actual area. Okay, what is the actual area? So that's that right there. That's the questions that we're going to answer right now. Okay, so here we go. If you needed to pause that, write down your questions and come back. So I'm going to start with A, and I'm going to graph this thing. Okay. I'm going from 0 to 4, 6. I'm going from 0 to 6, and then my function is 4x. So I'm going to say, I'm going to count this up. I'm going to have 1, 2, 3, 4, 5, 6. 6. So if I plug 6 into my function, right? If I plug 6 in, 4 times 6 is 24, meaning that at 6, I'm at 24. So I'm going to call this 24. And then I'm going to decrease by 4s, I think. I think that's going to be the easiest for me. Okay? Now, at 4, I'm just going to plot this, right? So 0, 0, 0. When I plug 2 and 4, I get 8. When I plug 4 in, I get 16. And I should have a straight line with a y-intercept of 0, slope of 4. Now, they're asking me for this area, the area of this triangle. before we actually do B, C, D, E, I think we should skip to F. I'm going to give you the answer right away. Let's find the area of this guy. Let's find the actual area. This is a triangle. How do you find the area of a triangle? It's 1/2 base times height. So what's the base of this? The base of this is 6. And the height of this, how tall is this? Well, this is f of 6, which is 24. The height is 24. So we find that the area is 3 times 24, which is 72 units squared, whatever the units are. So right now we know this whole thing is 72 units squared. I don't want to keep any answers from you. So the first thing they ask us on on approximating these subintervals is to break it up into 3 subintervals, meaning 3 equal parts. Well, 6 divided by 3 would be 2, right? So I'd make a subinterval here, okay? Now they want me to do this with left endpoints, meaning from here to here. Here's my first one. Up, here's my first interval, my second interval, my third interval. And I'm asked to find the area of this. Now, the area, right, is going to be my base. How much is my base of all these? The base of all these is going to be 2. My base times the height. How tall is this one? Well, that's going to be f sub 0. Plus the base of this, 2, times f sub 2. I'm going to plug 2 in and I'm going to get out 8. So I'm just going to write those so you see this, because the book looks kind of scary. They don't just tell you the answers. But they use all this notation. So if I plug 2 in, I get out 8. That's the height of this rectangle, plus 2 times f of 4. Okay? So when I plug 0 in, I get 0. So this is 0, plus f sub 2, this is 2 times 8, plus 2 times, how tall is this one? This one's 16 units. So we get out that if we have 3 subintervals.
Please bring that folder.